Oh. How do I change this? There we go. Okay. Oh my gosh. Number of waves split in an array. Given zero index integer array nums length n, nums contain valid split at I. Hmm. Oh. I see. Okay. Hmm. Okay, we're gonna keep a sum. Prefix sum. Okay. Dang it. What the heck am I doing? Jeez. Bruh. The 100th test case out of 101. Oh my goodness. Doesn't make much sense, actually. Oh no, not that. What's wrong with this? Is it time limit or it's the wrong answer? Bruh. Is it just incrementing by one? It is. Actually, I don't know why this doesn't work. Hmm. What the heck is happening? I don't get what's wrong. Like, how am I supposed to figure out what's wrong with this? Especially if it's the second to last test case. Everything should be bigger. If it all increase or decreases by one, everything should be bigger. So it should be the size of the array, but yeah, I don't get that. 10,000 counter. Oh, I definitely know why. It's totally this. Oh my gosh, of course. Really? Why? Literally, what's the point of that? What is the point of that? There's absolutely 0 point. Oh my god, it's so stupid. I forgot about overflow. Optimized? Does you say please do not demotivate the beginner. How long did it take? 14 minutes for me? Jeez. Okay, sliding window maximum. I think I just don't know this. Wait. Yeah, oh, I don't understand the, I can't even write it either, so. I'm just gonna look at the submission, copy it, and then try to understand it. To make a deck. User deck. I'm not gonna lie, I'm not following this. Okay. Deck. We'll make this the deck. Deck is empty. Both these fail. We offer I. What's that I? 1. Deck is not empty. I minus peak first. I minus 0. So 1 minus 0 is greater than k minus 1. So this is checking if we reached the k limit. If deck is empty, nums.deck.peak last. Deck.peak last is 1 less than 3. Yes, it is. Poll last. So we get rid of that. And then we're going to append 1, 3. And this fails. K minus 1. We're not there yet. So now we're on -1. We haven't satisfied this condition. Doesn't satisfy this condition. Offer last. So then we have 2, -1. And now I is greater than or equal to k minus 1. So the output I minus k. 2 minus 3 plus 1. 2 minus 3 is -1 plus 1. Okay. Deck.peak first. So output equals 3. Okay. -3. Peak first. What the heck is happening? Peak first. Deck to k minus 1. Oh, I minus deck. So we're at 3 minus 1 is greater than 3 minus 1. 2 is not greater than 2. So we don't do that. Nope, this just fails too. -3 is small. So adds -3. Oh my gosh, what is happening with my mouse? So then we add 3, -3. Peak first, this is still 3. Okay, so next time around, we are at 4. 4 minus 1 is greater than, so we pull this. And then, do we peak last or peak first? We peak last. while. Okay. So now we're at 5. 5 is greater than all of these, so then we do 4, 5, 5. We had 3. First condition fails, second condition fails. 5. We're at 6. First condition fails, second condition fails. Oh wait, no. First condition fails, but second condition does not. So we add 0, 1, 2, 3, 4, 5, 6, 6. Which will be right here. And then we run to 7. We get rid of this. We run into 7. Okay. My mouse is going crazy. I think we're chilling now. Oh my gosh. So we have a deck with integers in it. Oh my gosh, deck with integers. Then we have output equals new int nums dot length minus k plus 1 for in I equals 0 has to be less than nums dot length. So if deck is not empty and deck or nums I minus nums deck dot peak first is greater than k minus 1. Deck dot poll first. If deck dot is empty and nums deck dot peak last are less than nums I, deck dot poll last, and this is a while, and then if deck dot offer last I, if I is greater than or equal to k minus 1, and num or output I, output I minus k plus 1 equals nums deck dot peak last. Might be peak first. Yeah, there we go. Oh, my body's dead. I need to be able to explain it though. I haven't explained it yet. So we keep deck. Yeah, we have to keep a deck. So we'll make a deck and we'll make a deck. We'll store the greatest values at the front, and then we'll add So we'll store a deck. We'll use a deck. We'll iterate through all these values. If the decks, we'll use a deck. We iterate through all these values. The deck will store the indexes. If the The deck will store the indexes and only stores the index of I minus k plus 1. Or no, I minus k. Yeah, I minus k minus 1. So we have a deck that stores the indexes of all these values, and the deck will only store values that are up to k or I minus k minus 1, and it has a I'm going to make it maintain monotonicity as we iterate. So we're gonna C1, we're gonna C1, put it in the deck. C3, pop 1, put it in the deck. C negative 1, don't do anything with it. So now we have a deck that only has 3 in it. C negative 3, don't do anything with it. Actually, I don't know if that's true. I think we do something with it. Deck, injure deck. Output equals. Comes out like minus k plus 1. So we iterate through all of these. So we have 1. We have 1. We add 1. Then we add 3. Or we add 1. Then we're on to 3. We pull 1, add 3. Then we're on to negative 1. We add negative 1. We add negative 3. And then we're at 5. We pull this. We're at 5. Oh yeah, we're at 5. We pull this, but we also pull these two because 5 is greater than those two. We pull this because it violates this, but we pull these two because it violates this. And then we have 5. 3. We offer. 6. 6. We pull 5. We pull 3. Go to 6. And then 7. We just offer that. Yeah, so we'll create a okay. So we use a deck to store a monotonically decreasing values. Is that even the proper use of the word? Yeah. So this is a monotonic deck that stores only decreasing values. We we pull the front of it when we have more than k values. That's so wrong. So we have a monotonic deck that decreases. We pull values when I is greater than k. I is We pull values based off of whether the current iteration is within k of the items in the array. So we have a monotonic deck that stores items. We have a monotonic deck that decreases. We're going to iterate through all these values, store their indexes, and get rid of items in the deck based off of whether the current index or any indexes are outside of the current index minus k, and if we have encountered a larger number than is in the deck. So if we encounter a larger number that's in the deck, we're going to pull all of the values that are larger than it. Yeah, so we are going to make a monotonic deck, and this is going to be strictly decreasing. We're going to make an output array that's nums.length minus k plus 1, which will be the amount of k rolling groups that are possible in the nums array. And then we're going to iterate throughout the entire nums array. If the deck is not empty and the current index of the current index that we're at subtracted by the first index in the peak is greater than k minus 1, then we're going to take the deck and pull first. We're basically just checking if the first index violates the k group size. Then, while the deck is not empty and the current number at the end of the deck is less than the current number. So if we iterate from 1 to 3, when we process the number 3, we're going to see that, okay, 3 is greater than 1, so we're going to pull 1 there. Because it breaks the monotonicity of the deck. And then we're going to append -1, append -3, and when we encounter 5, we're going to pop this or pull this because it violates the k group size. And then we're also going to pull -1 and -3 because 5 is greater than that, which is why we stick it into a while. And then I take deck and I offer last I. And if the current index is greater than or equal to k minus 1, then the value for the output of I minus k plus 1 is going to equal nums deck.peak first, because that will be the largest value. And then we're going to return output. Okay. That happens in O of n too. I'm doing word search 2 first. I am not doing. Oh my gosh. I'm not doing reverse nodes in K groups. I think I know how this works actually. So we're gonna make our output variable. Oh my gosh. Okay, I should explain it first. So basically, what we're gonna do is we're gonna iterate through each cell in this grid. We're gonna make, actually before we do that, we have all these words. We're gonna make a try and add all the words to the try. Then we're gonna iterate through each cell, and if it starts, or what's it called, we're going to run DFS on it based off of, we're gonna run DFS on it and check whether any paths exist within the try. Yeah, that's basically it. So we're gonna create an output array. We're also gonna create a try. Okay. And then for every word in words, we're gonna take the try and add the word. And then we're making our output. And then we also need a visited array. Okay, and then we're going to iterate through each cell. And then we are going to run DFS on ij try.root board visited and output. And then we're going to return output. Okay, let's make the try. So we're going to make class try, and we're going to have an instance field of the root, and that's about it. The constructor will be this.root equals new try node, and then we will have public void add with a word as the parameter. And how we will do it is we will take a try node, call a node and make it the root, and then for every character in the word, are these all lowercase? Yeah. So for each character in the word, we're going to make an index, and it's going to equal word.char at I minus a. If the node does not have a child, or if the node's child at that index is null, the node's child at that index is going to equal a new try node. And then the node is going to equal that child. There we go. And then after the loop, we're going to make node.end equal to true. So then we can make our try node class. This is going to have an end variable that's a Boolean. And then it will also have an array of try nodes called children. And the constructor will construct everything. So the end will be false. And this dot children will equal a new try node of 26, a new array of try nodes with 26 indexes. Because that's how many letters of the alphabet there are. And then we will DFS. So we're going to say public void DFS. We have the row, the column, the node, the board, a visited array, and the output. So if the row is less than 0, or the column is less than 0, or the row is greater than or equal to the board.length, or if the column is greater than or equal to the board's row.length, then we're going to return something. Nothing. Then okay. Then what are we going to do? If we have visited this tile, we're going to return yeah, and then we're going to calculate, well, actually we're going to mark this as visited after that, after all the validation. And then we are going to take the current character and create an index out of it. And if node.children index equals null, no, if it does not equal null, node equals node.children index, and we have that value. If the node has reached its end, then we're going to take the output and add, oh shoot, I gotta redo this. So instead of making a Boolean end, we're gonna make a string word. This dot word equals, actually we don't even need anything. Actually, this dot word equals null. How about that? So then, in the add method here, instead of node.end being true, it's gonna be node.word equals word. So by doing that, we can say if node.word does not equal null, output is going to add node.word, and node.word is going to equal null. And then we're going to run DFS on everything. So row plus 1, call node board visited output. And we're going to keep on doing it. Row minus 1, call node board visited output. DFS row call plus 1 node board visited output. DFS row call minus 1 node board visited output. And then visited row call equals false after the DFS is done. So I'm extracting this out and just revalidating. So if node.children.index equals null, then we're just going to return. And I think that will make me mark it as visited after the fact. Yeah. And I think we are good. Wow. First try. That actually makes a lot more sense now that I walk there. Okay, that was pretty easy. All these are hard. Let me do median from data stream. I'll do this tomorrow. I'm just really tired. Okay. So the key to this is to have two priority queues. One that stores the left half and one that or they both store half, right? But yeah, they both store half. I don't know where I was going with that. We can add all the numbers, and then when we can find the median by comparing the top of both of the priority queues. So we can make a public priority queue that stores integers called lower, and then we can make a public priority queue that stores integers called upper. This dot lower will equal a new priority queue, and it will be a max heap priority queue. Shoot. B minus A. There we go. And then this dot upper will equal a new priority queue, and it will have a min heap. And then yeah, we're fine. We will write add num. So to add a number, we're going to take this dot lower and offer it to the lower, the number to the lower. Then we're going to take this dot upper and offer the upper priority queue this dot lower dot poll. And the reason why we do this is because this number, we don't know where it's going to be within the two halves. So we're going to sort it on the lower half and then sort it on the upper half. Then, this is where I get tricked up. If this dot lower dot size is less than this dot upper dot size, this dot lower is offered this dot upper dot poll. So we do this to make sure that if there are two types of medians we can have. We can have an even median. We can have an array with an even number of add num operations or an odd number of add num operations. If it's odd, there's a clear defined median. If it's even, that means we have to make a calculation for the median, which is the average between the two values nearest to the median. So if this dot lower dot size plus this dot upper dot size e mod 2 equals 0, that means it's even. Otherwise, it's odd. If it's even, then we're going to return this dot lower dot peak plus this dot upper dot peak and divide it by 2.0. If it isn't, we're going to return this dot lower dot peak because the lower will always get the median. And then we run. And it's not right. I'm dumb. I'm very dumb. We need to flip this. I know exactly what's happening. This dot upper dot. Okay, scratch everything I said. Lower dot pull. Okay, so we actually want to store the median in the upper, not the lower, because the upper is a min heap, and if it's smaller than all the values, it's fine. If it's larger than all the values, then it will be sorted. For the lower heap, if it's small, it'll be sorted, but if it's too big, we don't know if it's bigger than any of the values in the upper. So we need to prioritize the upper because why? Oh, because it will sort the upper half. What? What? I had it right? Wait, I'm so confused. Oh. They have to equal each other. This is a better way to do it. Okay, actually it doesn't matter. Like, I wonder if I do this. Oh, it's because the upper is prioritized here, so we'd have to flip these as well. So this should do it correctly. Yeah. Okay, so the reason, like, we can do public priority queue integer lower integer upper lower equals new priority queue b minus a upper equals new priority queue b minus b. So add num this dot lower dot offer num this dot upper dot offer this dot lower dot pull. So the reason why we have to do the order in which you do this matters, because upper will always have the odd. So this dot lower dot size, we want to make sure that the lower has the median in that way. Because if we do it the opposite way, then we're not sorting it properly. Or if we do it the opposite way, then it'll never hit. So this dot lower dot size, this dot upper dot size, this dot lower dot offer, this dot upper dot pull. And then for this, if this dot lower dot size equals this dot upper dot size, return this dot lower dot peak plus this dot upper dot peak divided by 2.0, else return this dot lower dot peak. Plus. Cool, we're done.